Welcome back to CS479 Machine Learning for 3D Data. So last time we were discussing some ideas in terms of like how we can make the neural net as an implicit function. So it was actually very simple, the idea that we are basically just making a neural net that takes the coordinate in the 2D or the 3D space and basically returning either the sign distance or the occupancy as kind of the value for each of the point. And for that, basically, to make this kind of the implicit function, we could consider either basically predicting some kind of a sign distance function or the occupancy function as well. And for both of the cases, we could basically choose the different loss functions. Actually, the main part for the last lecture was basically how we're gonna basically make this such kind of neural net, especially for some multiple shaped cases. So especially if we want to make some kind of implicit decoder, they can basically decode not only a single shape, but the multiple shapes. We could simply basically combine some kind of the encoder and basically take the latent feature of that each of the input as kind of the additional input in the neural network. And the other way around was basically making some kind of the meta function that is basically predicting the parameters of the neural net, which becomes the implicit function for each of the shape. So this was basically very simple the idea, and also basically the good thing of this kind of like input decoder was that basically the architecture of the neural net could be very compact, which means that we can basically encode all the kind of the different shapes into some very small neural net. And while basically also making the compact neural net, we could also decode the shapes with the fine details. And also the good thing was that we could basically easily vary the resolution of the output shapes. So that's a really good thing, especially compared to the some other cases that we are using some kind of the 3D the convolution neural net, basically predicting some kind of the voxel wise the values for those kind of the cases. And also for the point cloud decoder, when you basically make the point cloud decoder, as you have done in the assignment 1, those are the cases that we are fixing the resolution of the output. But for the implicit decoder, would you please mute if you are not asking any questions? Yeah, so especially in the case of the like implicit decoder, the good thing was that we can basically easily vary and also increase the resolution of the output. So that was really kind of good thing. And also there was basically no limitation in terms of the topology of the shapes. So we could also decode some kind of the very complex shapes with some lots of the holes and the gaps in the shapes. The only downside was basically it was the case that we are predicting the per point values. So if you want to generate the full shape, basically it takes lots of the time in terms of basically getting all the values for each of the points. And also for typically the case that we are getting the implicit function, to be able to use the output in so many applications, we also need to convert the implicit representation into the many other representations. So that would be also kind of the some of the downside of this idea. And also the other thing that we discussed last time was basically how we can also make some kind of the better the architecture in terms of the, especially in the case that when you're taking the images as the input. So in the case that when you have the image as the input, basically some 2D to 3D, the reconstruction, the situation, we could consider basically the spatial the alignment of the 3D and the 2D in terms of that we are not just taking the global the latent code of the entire the input data, but we are taking the corresponding the pixel in the 2D space in terms of like just getting some kind of information along the all the array in the 3D space. So for example, if we want to basically get the some either the sign distance or the occupancy the values along this array, you can basically take not only some global information but also the local information of the corresponding the pixel in the 2D space. And by leveraging this kind of the spatial alignment, actually we could achieve some basically the better results. So that was the idea that we could basically consider in the case of like 2D to 3D reconstruction. And for today and also for the next week, we're gonna discuss more this idea in terms of like how we can even improve the quality of the 3D reconstruction from the cases, especially when you have the multiple images. So that's what we are going to discuss for today and the next week. And also, when you basically make some kind of the implicit decoder, what we also discussed last time is that it's also very important to choose the right activation function. So what we discussed last time is that if we choose the typical activation function like ReLU or some other the activation the functions, those are the cases that the first, especially the second derivatives and the higher order the derivatives basically become zero. While the function that we would like to basically reconstruct would be typically the cases that we are having some very complex the functions in terms of that there the derivatives never become zero. For those kind of the cases, actually, we could consider basically using the sinusoidal function as the activation the function in a way that we can see way faster the convergence of the function like this. So this was also one of the examples that we are not only precisely reconstruct the input the function, but also basically getting some quite good the reconstruction the results of the derivatives as well. So even when we provide only the information about the given the function, we are actually getting some quite good results in terms of precisely matching the first and the second derivatives of the input function. And even we could the other thing, the other way around in terms of that, when we only provide the first derivative information, actually we could also see the results that the neural net is basically kind of like solving the Poisson's equation in a way that we are basically getting the input function like this. And we also could see the same results, not only for the 2D reconstruction, but also the 3D case as well. So this is the case that, so you can say that this is the case that we are basically having only the surface normal information. Basically, the first derivative of the impulse function is basically kind of the surface normal information. So given the surface normal information, we are basically reconstructing the impulse function in a way that the first derivatives becomes the same way given the normal information, while basically giving some other kind of the constraints in terms of that, we are basically getting some kind of the values like close to zero over the surface of the shapes, and getting deviating far from the zero for the area which is not on the boundary of the shapes. So for those kind of the cases, compared to the other case that we are using some typical deactivation function like the ReLU,
a single fully connected siren with 5 layers and 1024 hidden units may also faithfully represent a full-scale room, while a ReLU network fails to faithfully reconstruct the room, as illustrated by the inability to fit the curtains, the bowl on the table, or the feet of the sofas.
Yeah, so these are the results. And also, if we discuss a little bit more about like this idea, so basically, there are actually many kind of the similar ideas of basically using this kind of the periodic function as for some kind of the mapping of the input. So the idea in this work, the Fourier feature network, is kind of doing the same thing, but it's basically not basically using the activation function of using the sinusoidal function as activation function, but it's actually mapping the input of the network to this kind of using some kind of as the features using some periodic functions like this, and feeding this as kind of the input to the neural net. So before you basically feed the input, the data into each of the layer in the network, we are doing some this kind of the mapping with the cosine and the sine function like this, in a way that the output of each of the cosine, the sine, the function becomes the input to the neural net. This is almost the same idea, but not using the periodic function into the activation function, but as kind of the sort of the pre-processing of the input data for each of the layer. So this is kind of typical the things like instead of like directly feeding the input data, for example, like here is the x, y, the coordinates. If we basically make some kind of the implicit decoder of the images, then this would be the case that we are taking the 2D coordinates as the input. So instead of like directly just feeding these 2D coordinates to the neural net, we are first mapping these x, y, the numbers into this kind of the outputs of the sinusoidal the functions in a way that we are not only increasing the dimension of the input, but also mapping the input with the cosine and the sine function. Have you seen this idea in the neural network? Actually, this is quite common idea that you might see when you might learn from some other deep learning related things. if you took any deep learning courses, you might see this. Yeah, actually, this is the same with the positional encoding in the transformer. So if you know the transformer, the architecture, which is quite, the common architecture these days that everyone uses. If you see the architecture of the transformer, the architecture, you can see that there is the kind of the part of the positional encoding, which is exactly doing the same thing. So this is basically the idea that has been used not only for some kind of like implicit decoders, but for many other architectures in terms of like mapping the input to the neural net into some kind of the outputs of the some sinusoid of the functions. So this is very common the idea in many kind of the neural net designs. So if we briefly see some kind of the theoretical background, obviously there is no any kind of like theoretical guarantee here. These are some kind of the analysis based on the lots of the assumption in the neural network. But basically, let's see what basically this means. That what's the meaning of like basically mapping the input to the neural net into some kind of the sinusoid of the functions. So what we are going to basically see is that the neural net, like the trained neural net, is doing some kind of the kernel regression. So let's think about the setup of the kernel regression like this. So given some kind of the pairs of the input and the output data. So here basically xi is basically input to the function, and the y is basically the desired output for each of the input xx. Basically, then the problem of the kernel regression is basically finding such kind of the function f with some kind of the given the kernel here. In terms of that, we are basically getting the best value of the alpha here for each of the data point xi. In terms of that, we can get the approximation of the desired output for each of the x. So this is basically the basic setup of the kernel regression. Actually, we have seen this setup before. Do you remember when we have seen this setup before? So kernel regression is basically very general setup in terms that we are having some kind of data point xi, and we have some kind of the output that we want to see for each of the data input point. And then basically, given the kernel function decay here, we are basically getting some best value, the alpha, for each of the data point in terms of basically getting the best approximation in terms of that the output of this function becomes the same with the output that we want to see for each of the data point. And actually, we have seen this before in the case of like the moving least squares. Do you remember that we discussed this idea? We did not discuss SV. Yeah. So in the case of like basically getting the implicit function from the point cloud, we discussed the multiple ideas for that, right? The simplest idea was basically just finding the closest point and measuring the distance. Measuring the distance to the each of the points. Let me just quickly check my. Yeah. So yeah, the other idea was basically the moving least squares, which could be basically interpreted as the kernel regression. So in the case of like getting the implicit function from the point cloud, the data points, the x was the points in the 3D space, right? And the y was basically the output of the implicit function. So in the case that we are getting the sign distance function, the y for all the points becomes 0, right? So we are basically getting this kind of the alpha values here with the given some kind of the kernel function in a way that we can basically approximate all the signed distance for each of the point. So that's kind of the same case, right? Actually, we have seen this before. And then if you recall the ideas of like the kernel regression, do you also can you also basically guess what happens if we have some kind of the wide kernel or the narrow kernel K here? So K basically determines kind of the weight, right? For each of the query point X here. from this kind of query point to some kind of the neighbor, the point, the xi, k basically determines some kind of the weight. How basically much kind of the weight we put for each of the kind of the neighbor points in terms of like deciding the value for the query point, right? So basically, wider corner means that we basically consider the wider range of the neighbor points. We are giving some kind of the more the weights, some kind of the some points that are basically far from the query point. The narrow basically corner means that we focus more on some kind of the narrow the range of the neighbor the points, right? We are not basically giving some kind of the weights to the some kind of the points that are far from the query, right? So depending on how we control the width of the corner like this, whether we make some kind of wider corner or the narrow corner, what will be kind of the expected output that we're going to see. Yeah, so typically what we gonna see is basically results like this. So these are basically two cases that we are having some kind of the wider corners here. The first row is the case that we are having the wider corner. In the 1D case, basically, this graph shows that we are basically giving some kind of weights to some neighbors like this. And we can also have this kind of the narrow the corner like this. Then as we basically have some wider corners, we're gonna see some more the basically smoother function like this, while basically not precisely basically aligned with some kind of the given the data points. So this is kind of the case that we are seeing some kind of the smoother function, but with some kind of the less precise kind of the reconstruction of the given the data points. And as we basically make some kind of the narrow the corners, we might be able to get some kind of the more the precise the outputs for each of the given the data points, but it's basically overfitting, right? We are basically getting some more kind of the fluctuating the function in terms of that we would be basically overfit to the all the given the data points, which means that when it basically interpolates across the data points, the values that we're gonna get in the interpolation may not be basically accurate. So there are basically the pros and the cons. As you basically increase the width of the corner, we may not be able to get some kind of some precise the reconstruction results, while basically getting some kind of smoother function. So not overfitting to the input data. But basically, if we basically make the corner size to be the narrower like this, then we are seeing some kind of the overfitting the outputs like this. So these are the basically the cases that we are doing some kind of the underfitting. Sorry. And the overfitting, right? Depending on the corner size. So that's basically what we can expect to see in the corner regression. And what people have shown in some kind of based on some kind of theoretical analysis is that with some kind of the loss of the assumption here, we can think like training the neural net, training the typical neural net is kind of like finding a function which basically converges to the solution of the corner regression with the corner, which is called the neural tangent corner. So we are not going to get into the older details, so like this, the neural tangent kernel. But basically what we can see is that this neural tangent kernel is basically the dot product kernel, which is defined like this. So when you basically have the two inputs like this, given any kind of the two inputs, the kernel function is basically defined as kind of the dot product of like these two. So this is kind of the analysis that people have done with the neural net for some kind of the loss of the assumption with this kind of the given the neural net. So for very special cases, we can see that the trained neural net is the case that we are finding a function which becomes the solution of the kernel regression with the neural tangent kernel, which basically takes the dot product of the two input as kind of the input of the function like this. So then what we can see is that now what we are doing is that we are doing this kind of things. So before we basically feed this input, the data into the function, what we do is that we are first like mapping this into some kind of the sinusoidal function like this. Then from the trigonometry rule, what we can see is that the dot product of these two vectors, the output of the basically positional encoding, can be basically written like this, which means that we are feeding this as the input to the neural tangent kernel, right? Makes sense. So what we can see is that while the typical neural net was the case that we are basically learning the function with the kernel that takes the dot product as the input, if we basically first map all the input data with the sinusoid of the functions, then what we can see is that it becomes the case that we are basically making a function with the kernel that now takes the difference of the two data points. So we can see that now we are basically learning a function with this kind of the kernel, which is now taking the difference of the two data points. So that's basically the idea here. And you can see that this is basically sum of this kind of the cosine function. So you can see that actually this is basically like compositing some multiple the kernels, different kind with some kind of the different the kernel the width. And the width of the kernel will be basically determined with this basically the b, basically the frequency of the cosine function. So which means that when you basically map the input data with the cosine and the sine function here, we can control the composition of the kernels, especially the width of each of the kernel based on the frequency of the cosine function, the cosine and the sine function that we are using. So what we can see is that, let me show this first. So what we can see from this graph is that this is the case like how much basically weight that we put for each of the cosine and the sine functions. So if I just go back to the previous slide, well, let me just quickly go back to here. Yeah, here basically this is the case that for each of the cosine and the sine function, we can set some kind of the weight, right? A becomes kind of the weight, basically, how much basically the weight that we're gonna put for each of the kernel function with the different width of the kernel. And what we can see is that this orange line here is the case that we are just giving some kind of the this is the case that we are giving the high weight for all the cosine and the sine functions, while this kind of the purple color is basically decaying the weight for the higher frequency, the cosine and the sine functions. Then what we can see is that as we basically decrease the weight for the higher the frequency the functions, we are seeing this kind of the wider the range of the kernels, which means that we're gonna see the results of the underfitting, right? But as we basically increase the weight for the high frequency the functions, high frequency basically, the cosine and the sine functions, we're gonna see the results of basically having some narrower the kernel in this specialty domain. In terms of that, we're gonna see the results of the overfitting. Make sense? Yeah, so this is kind of the results of that, when we have some kind of the case that we are having some lower the weight for the higher frequency, the cosine, the sine functions, we see this kind of the underfitting results like this. And as we basically increase the weight for the higher frequency, the cosine, the sine of the functions, we're gonna see basically results of the overfitting like this. So which means that there will be some kind of a sweet spot in terms of like when you basically control, and the weights for each of the cosine and sine function, and when you basically find the best the ways, we're gonna see kind of the results, which is basically not underfitting and the overfitting to the input data. And this is basically some results in terms like learning some kind of the implicit function for the 2D image. So when you basically learn a implicit function 2D image, depending on like how we control the width of the kernel, as you can see here, you can see some kind of results that we are seeing now the underfitting results, right? Blurring out the image, or we can see some results or like overfitting to the image, having some kind of noise. So question: are the ways of design cosine features learnable then? Yeah, it's not learnable, and actually you can set these numbers. So if you think that the function that you're gonna learn is kind of the function that basically include lots of some high frequency, some kind of details, then you can basically increase the weight of the high frequency the functions. Well, if you want to basically learn some kind of the smooth function, if you know that the alpha function should be smooth, then you can basically decrease the weight for the high frequency. So that's really a thing. So depending on like which function that you want to learn, especially there might be some kind of cases that you want to get some better results with the interpolation. Then which means that the function that you want to learn might be kind of a smooth function. Then for those kind of the cases, you need to decrease the weight for the high frequency, the cosine and sine functions. If you know that the function that you want to learn is basically very high frequency function, then you also need to increase the weight for the high frequency cosine and sine functions. Does it make sense? So this is really crucial, the details in terms of like improving the performance of the neural net. So we're gonna also get to this point, and this is also very important point when you also discuss the nerve in the neural rendering. So this is thing. Any other questions on this? Simple noise instead of some other bad effects like random results. Well, basically the overfitting basically means that we are basically really overfitting to some kind of samples that we are providing, right? So if we think about the process that we are learning the impulse function, this will be basically the case that we are randomly sampling the points in the 2D space and basically predicting the colors that we are providing for each of the sample points. And obviously the samples that we are providing may not be all the points in the image, but basically some kind of just the samples, right? So in the overfitting case, we are basically getting some very precise color values for those samples that we are providing the training time. But while even for some kind of the points, which is very close to each of the sample, we are basically not getting some kind of the good prediction because the function is overfitting. So this is why we are kind of like seeing some kind of results that we are having some kind of noise, random noise over this space. Any other questions? Same as is the width of the corner same as the size of the matrix B? Yeah, so actually there are two things. So what we can do is that, yeah, in this kind of the vector here, dA, you can really control these weights in terms of whether you're gonna basically set higher the weights for the high frequency functions or lower weights for the high frequency function. Well, the other way, more kind of the simple, the convenient way is that you can basically set the number of these cosine and the sine functions. So what we also typically say is that when you say that we are increasing the output dimension of the positional encoding, which means that we are using some more the high frequency functions. While if we say that if we decrease the dimension of the positional encoding, which means that we are only using the low frequency functions, then we're gonna, depending on basically the length of this vector, how many basically high frequency the cosine and sine functions that we use, we're gonna also see the results of the overfitting and the underfitting. Make sense? Yeah, we're gonna also see these results in the nerve case. Any other questions? Okay, so moving on. So let me switch to the next step of the slides. Okay, can everyone see my slide? Okay. Okay, so actually let's move on to the main topic for today. Actually, this was kind of things that we need to discuss earlier. But let's go back to the discussion about basically reconstructing 3D from the 2D. So we discussed the idea of the PyFu, which was basically pixel aligned basically implicit function that we are basically taking each of the features for each of the pixel in a way that we can basically predict either the sign distance or the occupancy of the points along the 3D ray. And this was the case that we are basically getting some kind of 3D from a single image. So while this idea could be extended for the multi-view images as well, this was kind of the case that we could get this 3D from the single image, right? Then what if like we have some multi-view images? Actually, the thing is that if we have some multi-view images, getting this 3D is not a problem that we need to really use the neural net. But as you know, basically, humans also have the two eyes. So with the two eyes, we can basically sense the depth, right? We can have some basically some kind of the sense of kind of the how much the object is basically distant from the eyes, right? Because we're having the two eyes. So basically, what we can do is that if we have like multiple views like this, and if we also know that where we are basically seeing each of the image like this, then from this kind of the two multi-view images, especially in the case that when we have some kind of the information about basically the corresponding the pixels here. For example, like if we know like we have this pixel here, and there's the corresponding the pixel, sorry, so let's get into, yeah, if we have like this pixel and the other the corresponding pixel here, then from the camera, the pose information, the camera information, what we can do is that actually we can shoot a ray for each of the pixel and find the intersection point, right? So we can actually not predict, but calculate the position of the 3D, the points, basically which is projected to each of the image, right? So this is like matter of like that we need to just calculate and estimate the 3D position, not to predict. So actually, this is kind of things that we are going to discuss for today. So even without the neural net, with some kind of the loss of the images, actually people could get this kind of the 3D reconstruction, the outputs. As you can see here, this is results that we could see in 2009. Let me replay this. Yeah. In 2009, reconstructing the entire Colosseum in Rome with all the internet images that people uploaded to the internet. So what you can do is that you can just like pull all the images, the photos of the Colosseum, and do some kind of 3D reconstruction without the neural net. And the basic idea behind this kind of technique is basically nothing but basically that we are basically getting some kind of the camera information like this and shooting the rays for each of the corresponding the pixels and basically reconstructing each of the point, the 3D point from the 2D information. So this kind of the process, basically having the two corresponding the pixels in the images and shooting the ray and finding the intersection, the points of the rays, this kind of the process is called the triangulation in the computer vision. So through this kind of the triangulation the process, actually we can do some kind of the 3D reconstruction. So here basically you need to see what's basically the problem that we really need to leverage the prediction, the power of the neural net, or what is basically the problem that we can just directly calculate and estimate from the given input data. And see, like without the neural net, actually even like about like 14 years ago, people even could basically reconstruct the entire city, like the entire the Rome, with lots of images like this. This is not something that we really need to use the neural net. Without the neural net, we can basically directly control the things like this. So you can find the library which is called the Colmap. There are basically lots of kind of libraries that are basically implementing all this kind of the technology which is called the structure from motion. And you can basically utilize this kind of library in terms of the making doing some kind of reconstruction of the 3D yourself. So really, I mean, you can just like take the photos of the your space and feed this kind of photos into the Colmap library, and you can get this kind of the reconstruction, the results. And this kind of the technology, which is the reconstructing 3D from the multi-view images, is called the structure from motion. Basically, getting this 3D structure by just basically moving the cameras, or the same thing can be called SLAM as well. The simultaneous the localization and the mapping. So these are kind of almost the same kind of the types of the technique. While the term the SLAM is typically used in the robotics, and the structure from motion is typically used in the computer vision. So what we are going to discuss today is basically the very basic idea about the structure from the motion. And obviously the thing is that to understand all the details for this, basically for the rest of the slides that we are going to discuss for today, you might need to have some kind of the background in the computer vision and the linear algebra. So if you have any questions for any kind of things, please let me know. Feel free to stop me. And also this will be very brief introduction of the structure from motion, which is actually a subject that basically needs like entire semester to discuss all the details. So we won't be able to discuss all the details, but I wanted to basically provide some kind of the very basic idea in terms of basically how we can do some kind of the 3D reconstruction from the multi-view images. And also I wanted to emphasize that reconstructing 3D from the multi-view images it's not a problem that we just need to use the neural net, but actually that can be done without the neural net in some extent, and we're gonna see how much we can do some kind of reconstruction. So this is basically the typical pipeline from the structure from motion. As you can see, there are lots of kind of the components in the full pipeline. So we're gonna get into each of the things. And before that, actually, we're gonna discuss the basic idea for the camera model. So before we go into this, how many of you took the computer vision course or computer graphics course? Raise your hand. Or if you did not take the computer vision or the graphics courses, let me know. Yeah, so if you did not take even either of the computer vision or the graphics course before, then this might be really kind of, very quick and brief introduction for everything. That might be too much to understand in a very short amount of time. But let's see. So to have some like better understanding for all the things, I recommend obviously you to take the computer vision or the graphics courses. But yeah, this is basically introduction of the things that you're gonna learn those kind of courses. So basically we're gonna have some kind of the mathematical models for the camera, basically how we basically model the camera here. So this will be basically the case that we are having the world coordinates. We have basically the X, Y coordinate in the world frame. And then also each of the camera, we're going to also have some kind of the camera frame as well. So if you also took the computer graphics course that I taught in the last semester, this is basically the concept of the frames, right? We are having the world frame and the camera frame, the I frame basically in the graphics. So we are basically having the world coordinates and the camera coordinates. And as we define the model view matrix and some kind of the matrix that we're transforming from the world coordinates to the camera frames, we can define some kind of some transformation matrix, which is composed with some kind of the rotation, 3D rotation, and the translation, which is basically transforming the world coordinates into the camera coordinates. And this kind of the information of the camera is called the extrinsic parameters, in terms of that it's not basically related to the camera intrinsic properties. So it's not about some lens information. It's basically information about basically where we put the camera with which orientation, right? We're gonna also have the intrinsic parameters, which is more about basically about the projection. So given some kind of the 3D points defined with the camera coordinates, if we just project all this 3D information into the 2D image plane for each of the camera, then we can consider basically having this kind of like multiplying the intrinsic parameters, this matrix. And typically this intrinsic camera matrix is defined as kind of this 3x3D matrix with the focal length information and also the center information. So this is the example without the distortion, but we can also consider like having some kind of the lens distortion with some kind of the cases. But this is the simplicity model, right? So what we can see is that basically mapping from the 3D in the world coordinates into the 2D in each of the image plane can be considered that we are basically multiplying this camera matrix, which is basically 3x4 matrix. So we are having the x, y, z some values, describing the 3D coordinates, and then we are basically multiplying the extrinsic matrix first in terms of we are first transforming the world coordinates into the camera coordinates, and then we basically multiply the intrinsic matrix in terms of we are basically finally getting the 2D the coordinates. So the thing is actually, while this small x indicates the 2D coordinates, we are having the 3 numbers, right? So we are for the small x here, we are basically getting the homogeneous coordinates. This is the case that we are treating this 3-dimensional vector as the same as kind of like this vector. So whatever number that we multiply or we divide by for each of the numbers in the vectors, we are treating them as kind of the same vector. And the reason for this is that we are introducing this homogeneous coordinates in terms of that this 3x3 matrix becomes the projection matrix. So while basically we are just like transforming the 3-dimensional vector into the 3-dimensional vector by just treating these small x as the homogeneous coordinates, we can see kind of the effect of like doing some kind of the projection, right? So basically having this like homogeneous coordinates and the 3x3 matrix K here, basically making some kind of projection from the 3D to the 2D. So this is basically very quick introduction for the camera model that you might familiar if you took any of the computer graphics or the vision courses. Yeah. Any questions on this? So you can basically think that this is the case that we are having the 3x4 matrix as the extrinsic the parameters, another 3x3 matrix as the intrinsic parameters, and we are getting some kind of the 3-dimensional the vectors, which can be basically divided by the last number here in terms of we are getting the final x, y, the coordinates in the 2D space. So having the projection from the 3D to the 2D. So this is what is the W. So we are basically having these 3 numbers here, x, y, and the W. And then when we divide this x and the y with the last value here, like this, then when we make the last value this to be 1, we are getting the real the coordinates in the 2D space. And the reason that why we are doing is that this is basically so when you have some kind of the normalized some coordinates, this is basically r t times x. So when you have this, then you can see that this times k becomes the 2D coordinates. And basically by the combination of like this multiplication decay and this kind of the some kind of the normalization dividing by the w, we can see the results of the projection from the 3D to the 2D. So we won't be able to get all the details of the camera model here. So if you did not take the computer vision or the graphics courses, you might need to basically see some details of the camera model there. But you can see that basically the camera, the projection basically can be the model as kind of the matrix form like this. So this is the like very basic the background. And given the structure flow motion, the pipeline, that what we are going to do, I mean, actually, there are tons of some kind of details and so many kind of the components that we can add. But if we see some kind of the some high level, the ideas of the structure flow motion, the pipeline, then what we do is that for each pair of the images, we first find some of the correspondences of the key points. So what we do is that we first find some kind of the important points like this that we call the key points, and then we are finding the correspondences of them. So that's the basic idea. Like we can use some kind of some very typical idea, like detecting some kind of the important points, the key points for each of the image, and for each of the point, we get some kind of the description, some basically the feature vector for each of the pixel. And there are also lots of the techniques that we can get some kind of feature vectors, like the shift and the SERP, and also we can use the neural net for this, which is basically describing each of the key points as some kind of the high dimensional vectors. And then we can basically find this kind of the correspondence across the key points by basically finding the points that are basically minimizing the difference, the features, right? This is a very conventional things. If you take the computer vision course, then you get this kind of this very basic idea. So in terms of we are basically getting some kind of the pixel-wise the correspondences for some of the key points. And obviously there might be some kind of the noise and the outliers, as you can see in the left side here. I mean, yeah, there might be some kind of the sort of the wrong estimations, wrong predictions of the corresponding points. So for those kind of the cases, there is also the technique that is called the rank set, which is basically also finding only the inlier set of the corresponding the point pairs. So the basic idea of like finding the inlier set is that we are finding a subset of all the corresponding points in a way that all the given the inlier dependencies can be basically expressed with some kind of the single the projection, the projective transformation in the 2D space. So basically all the kind of the correspondences of the pixels should be basically expressed with the single projective transformation from the 2D to the 2D image, right? So these are also the technique that people use. And so once we basically have all the pixel-wise the correspondence in the information, then what we can do is that from the pixel-wise the correspondence, we can estimate the camera pose. So we basically define, discussed the camera model in terms that we are having some kind of the world coordinates, and for each of the camera, that we are also having some kind of the camera coordinates as well. And here, basically, it's matter like how we define the world coordinates, right? There is no predefined world coordinates. We can choose whatever kind of frame as the world frame. So what people typically do, what we can typically do is that we can just set the camera frame of the first camera as the world frame. So let's just set the camera frame of the first camera as the world frame. Then what we are going to do is that we are basically getting some kind of the relative camera matrix, the camera information of the second camera from the first camera, right? Make sense? So we are having the camera information for each of the image. And what we are going to discuss today is basically how we get this kind of like the camera information, the camera pose information. This is the challenging part. But once we basically have all the camera information, then what we can do is that for each of the corresponding pixels for each of the image, we can shoot a ray from the 2D to the 3D space. So this is basically doing some kind of the sort of the reverse engineering, right? Actually, the output of these images were basically the output of the projection of the 3D to the 2D. So we are doing all the things in the reverse way, in a way that from the 2D, for each of the pixel, we are shooting the ray into the 3D space. Then if everything was basically calculated correctly, then what we're going to see is that these two rays of the corresponding pixels will be basically intersecting at one point in the 3D space, right? So we can see that actually this was the point which was basically projected into each of the 2D image, right? So this is basically how we get this 3D information for each of the images. And obviously this will not be only the case that we're having like just two images, but there can be some kind of the multiple other images as well, right? So in the cases that we will have some multiple images with all the kind of the correspondences of the pixels across the multiple images, we can do some kind of the joint optimization in terms like optimizing the 3D point, because these 3D points should be intersection of all the rays coming from all the different images, right? But while if we have some kind of some small noise in terms of like getting the correspondence or some the camera matrix information, then when you shoot the rays, these rays will not basically intersect at like one single point, right? So we are basically doing some kind of the joint optimization in terms of like optimizing all the camera the matrices of the images and also the 3D points as well. And this process is called the bundle adjustment, which will be obviously very computationally expensive the task, which is also basically very complex. The optimization, which is also very non-convex optimization. So this is the kind of the most challenging part. But basically, this is kind of the process that we are first finding the pixel-wise correspondence. Based on that, we are basically getting the relative camera pose information and shooting rays into the 3D space, getting some kind of 3D output. and doing some kind of the joint optimization of the 3D points and the camera D matrices. This is the very high level the idea of the structure from motion the pipeline. Any questions? Obviously, there are many other things that can be added into this pipeline. And also one interesting thing is that if we only optimize the relative camera poses, not with the 3D points, so we can actually, so this will be the case that we are getting all the relative camera poses for any pair of the images, right? So when you set the camera as kind of the world frame, we can get relative camera poses for the image, right? And any pairs of the images, we can get all this kind of the relative camera pose information. Then we can do some kind of a synchronization in terms of that. If you start from the camera A and going to the camera B and going to the camera C and going back to the original camera, then you need to basically come back to the original camera frame, right? So in terms of that, you can do some kind of some synchronization. And the interesting thing is that this optimization, basically doing some kind of synchronizing all the kind of the relative camera poses, is a problem that we can solve with some kind of the optimization. Even there is some kind of the analytic solution for this optimization. So it's kind of interesting things. The question here is that how do we control the viewpoint and the image? Well, basically, this is the case that we know we have the information. Yeah, you mean this distance? So the question here is that basically if we have some varying distance between the camera and the image plane, then the output of the 3D will be also changed, right? So those are basically some kind of the information that is given with the intrinsic parameters K. So it's basically a matter of how we get this kind of the intrinsic parameter for the camera. And actually, we are not gonna discuss details about the problem. So basically, getting the intrinsic parameter is the process that we call the camera calibration. Through some kind of a calibration process, actually, we can estimate the intrinsic parameters for each of the camera. But also the thing is that these days, for many kind of the digital photos, the digital photos also provide some kind of the intrinsic parameters as well. So we can also use some kind of the given information. But basically, once we have the intrinsic parameters for all the cameras, that will basically determine the final output of this 3D. Why the rotation make external walls does not? You mean here, right? Actually, yeah, that's a really good point. Actually, we can take not the L2 distance here, but some kind of the distance over the SO3 space. Then actually we're gonna get some kind of also better results. But here the thing is that as we have some sort of the simplified loss, then the problem becomes kind of easier. Actually, yeah, when you actually have the geodetic distance loss in the SO3 space, actually we can also get some better results. But depending on how we define some kind of objective function here, the way that we can solve this kind of optimization will be also be changed. So there are also lots of the discussion in terms of how we can solve this problem. Lots of interesting things that we won't be able to discuss everything here. But basically what we are going to briefly discuss for today is basically these parts. So as you can see, so there are 4 steps. We find some kind of the correspondences of the key points. So here, once we find the correspondence of the key points, from this we should be able to basically compute the relative camera poses. So we are going to basically discuss this idea, basically how we can do this. Actually, once you have the camera images, it's quite basically straightforward in terms of shooting the rays into the 3D space and finding the intersection. And this is very complicated, some kind of optimization, the problem that we are jointly optimizing the 3D points and the camera matrices as well. So we won't be able to discuss details of this. But what we are going to briefly discuss today is basically the idea in terms of how we compute the relative camera matrix from the one view to the other, given the 2D point correspondences. Any questions before we move on? Yeah. So this will be basically things that we want to discuss, lots of kind of the new concepts, new ideas. And if you are also more interested more in some kind of details, I also highly recommend you to check out the textbook, the multi-view geometry, and especially the things that we are going to discuss in the later the slides are basically described in the chapter 9. Okay, so let's go into some details of the epipolar geometry. So what does the mean of the epipolar geometry? So what we are going to see is that let's think about the case that we are having a point here in the, let's say this is like first the view. And then we are basically shooting a ray from the first camera through this 2D point. Right? So the thing is that we only have these 2D point information, which means that we don't know exactly where this point is projected into this 2D plane, right? So it can be this point or this point or this point, right? Any point in this ray can be the 3D point, which was projected into this 2D pixel, right? So which means that we can shoot a ray here into this 3D space, and any of the points here on this line can be the 3D points, right? So let's think about the case that we are now projecting, this ray in the 3D space into the other view, right? So when you have one single pixel in the first view, the projection of this ray in the first camera into the 3D space into the second camera is called the epipolar line. So what's the meaning of the epipolar line is that if we find the corresponding points from the x to the x prime here into the second the frame, the corresponding point of this x should be one of the points over the epipolar line. Okay, it's very clear, right? So what we can see is that if we have x, and if we know the corresponding point in the second the frame, the x prime, this x prime should be one of the points in the epipolar line. It's very clear, right? So that's by definition of the epipolar line. So what we can see is that, so now we're gonna use the homogeneous coordinates for the 2D points, which means that we're gonna have the 3-dimensional vector for each of the point, which means that the x prime also will be represented as the homogeneous coordinates like this. I mean, you can think that this is the case that we are having the 1 in the last part, right? And also we can represent this epipolar line with some line equation, having this kind of line equation, right? So if we just only take the parameters of this line, the equation A, B, and C, then also each of the line can be represented as kind of the 3-dimensional vector, right? A, B, C. Then what does this mean is that, the x prime should be one of the points, right, of the line L prime, which means that if we compute ax by plus c, this should be 0. Which means that if we basically represent each of the x prime and the L prime as the 3-dimensional vectors, their dot product should be 0, right? So far, so good. Nothing complicated here, right? So that's how we define the epipolar line. Then here the question is that let's think about these two cases. So when you basically represent all the 2D points and also the lines as kind of the 3-dimensional vectors like this, how can you basically compute the line which is basically joining these 2 points? So when you have the 2 points here, if we want to find the line that basically passes these 2 points, how can you calculate this line? And also the other way around as well. When you have the 2 lines like this, should be a point here. How can you find the intersection point of these 2 lines? So the things that we know is that if the point is on the line, that means that the dot product of these two should be 0, right? So when you basically see that each of the points and the line is kind of the a vector in the three-dimensional space, these two vectors should be orthogonal to each other, right? Being some kind of embedding of the lines and the points in the 2D space into the three-dimensional space. So which means that if we are finding a line, which vector in this three-dimensional space becomes like orthogonal to the vectors of these 2 points, what are such kind of vector? Like when you have the 2 vectors in like one space, if you find another the vector that becomes the orthogonal to these both of the vectors, then we can just like easily take some kind of a cross product of these two, right? Then this will be basically the line that we're gonna find. And it's the same here as well, right? So we are also finding a three-dimensional vector that becomes orthogonal to each of these kind of the 2 vectors, right? Then we can also find the intersection point as kind of a cross product. Here, apply as the three-dimensional vectors for the L and the L prime, right? So that's basically what we call as kind of the point and the line, the duality, in terms of the basically both the line joining the 2 points and also the intersection point of the 2 lines can be computed as kind of the cross product of all these three-dimensional vectors. Make sense? So let's keep this in mind. We're gonna use these facts multiple times. And also one kind of simple thing is that when you basically calculate some kind of a cross product, actually, this cross product can be also represented as kind of the matrix multiplication of this like skew symmetric matrix. So if we like compute like cross product of the x and the x prime here, what we can do is that we can basically make this kind of this skew symmetric matrix based on the given the three-dimensional vector x here. So when you have the x, y, w for the three-dimensional vector x, we can basically make this shape of the 3x3 matrix and multiply this to this vector. Then the output becomes the same. This is nothing but basically having some kind of the matrix multiplication form using some kind of the skew symmetric matrix. Make sense? Any other questions? Yeah, so here basically what we can see is that so actually one quick question is that so if we basically compute the determinant of this skew symmetric matrix, what would be the determinant of this matrix? Can you guess? So yeah, we're also not gonna get into the details, but basically, if you calculate the determinants like this matrix, this is basically not a full rank matrix, so it is not invertible. So this is basically rank to the matrix. So we're gonna basically go into that. So yeah, so that's basically the basic kind of the terminology that we're gonna see. So if we go back to the epipolar geometry, what we can also see is that we can also define the epipole as well. So epipole here is basically the point that is basically becomes the intersection between the line connecting the center of the 2 camera frames and then each of the image, the plane. See? So when you basically consider a line which is connecting the 2 camera centers, the intersection like this line with each of the image plane becomes the epipole. So why we basically care about this epipole is that if we see all the epipolar lines coming from any random point in the image plane, what we can see is that every epipolar line coming from any point on the other view should basically pass through the epipole. Can you guess why? I mean, this is quite obvious, right? Because we are projecting this ray into this plane, right? This is the ray that we are shooting from the center of the camera, which means that basically all the ray that we are going to basically shoot into the 3D space, we will be basically starting from the center of the camera, right? Like this. Which means that however basically you make the ray from the camera center, obviously the projection of like this camera center to the other image plane should be one of the points of the epipolar line. Make sense? So you can think that basically epipole is a point which is also basically intersection of any arbitrary two epipolar lines in the image plane. So if you draw any kind of the epipolar lines in the image plane, the intersection of like these epipolar lines will be basically this epipole. So this is basically basic the terminology of the epipolar geometry. Any questions on this? It is clear? So based on this, actually, we're gonna introduce like a few more the concept. So one thing that we're gonna basically see is basically the fundamental the matrix. So now we are considering the case that we are having some kind of the pixel-wise correspondences, right? So we are having some kind of the corresponding the points that we know in the two the views, two images. And then based on this, we can define the fundamental the matrix F, which basically 3x3 matrix that satisfies this. So when you have basically the corresponding the 2D point pairs of the x and the x prime in the different views, if we find a matrix F that satisfies like this constraint, then this basically the matrix becomes the fundamental the matrix. It is clear. And why do we consider this fundamental the matrix? I mean, this fundamental matrix has some kind of a lot of interesting the properties. So basically, what we can see. So for any kind of the point x here in the one view, if we compute the fx, then what do we get? Can you see? Question. So if we have like any point x in one image, then if we compute fx, what will be this fx? Yeah, this fx basically becomes the epipolar line, because we know that x prime, and the dot product of the x prime, the corresponding the point, and the L prime should be 0, right? So what we can see is that basically the multiplication of like this f to the any of the point becomes the epipolar line. So you can see that actually this f is basically a function that basically shows the mapping from the point to the epipolar line. For any point in one view, if you want to see the epipolar line in the other view, then you can just like compute the fundamental matrix, right? Okay. So this is the case that we are basically, let's say like we have the image A and to B. So from the image A, we have the point X, and we want to find the epipolar line L prime in the image B, right? And this mapping from the image A to image B is basically described with the fundamental matrix F, right? Then given this F, here the question is that what would be the fundamental matrix of the other way around? If we have the fundamental matrix from the A to B, what would be the fundamental matrix from the B to A? Actually, it's quite straightforward. I mean, you just need to take the transpose like all the things here. Then what you're gonna get is the x prime times f transpose will be x transpose, right? This will be 0, right? Then this will be basically f transpose will be fundamental matrix that you are mapping from the B to A, right? Same thing. It is clear. Yeah, so then also what we can see is that for any point x, now what we can see is that f times the x becomes the epipolar line, right? And we also know that any arbitrary epipolar line should contain the epipole E prime here, right? So this means that for any epipolar line, L prime, E prime transpose times the basically L prime should be 0, right? And then E prime transpose should be basically Fx equals 0. Can we write this? Fx 0. For any x, whatever x you choose, this should be 0, right? If you want to satisfy this for any arbitrary x, this means that this should be 0, right? So how we can find the epipole? So basically, given the fundamental the matrix, the F here, we can find the epipole as kind of the vector that satisfies this. So this basically means that the epipole, the E prime, becomes the the null vector of the given the fundamental the matrix. And also the other way around is the same. We can also find the epipole, the point in the first view image as kind of the right null vector. So what we can basically see is that the fundamental matrix gives them all the information about the epipolar line and the epipole, giving all this kind of information of like how the point can be mapped to the epipolar line, and also like how we can find the epipoles in each of the images. It is clear? Yeah, so based on that, we can also see the kind of similar things for the some normalized coordinates as well. So what we have seen is that, like, given some 3D point, we could basically first transform this with the basically Reed's body transformation, the rotation translation, which was basically some extrinsic parameters, right? Extrinsic parameters. And then we are basically first transforming the 3D coordinates in the world frame into the 3D coordinates into the camera frame, right? And then we are multiplying the intrinsic matrix in terms of getting the points in the 2D plane, the image plane, right? But basically, we can consider some kind of the points before we multiply the intrinsic the matrix. So after just like transforming the world frame the coordinates into the camera frame the coordinates, we can consider those as kind of some normalized the 2D coordinates, right? Into basically the coordinates in the camera frame. Before we do some kind of the multiplying the intrinsic the matrix. And with this kind of the normalized the 2D coordinates, we can also compute the define the same thing, but with the normalized coordinates. And this is basically called the essential matrix. So this basically looks exactly the same with the fundamental the matrix, but with the normalized to the coordinates, which is basically the coordinates before you multiply the intrinsic the matrix from the camera frame the coordinates, right? It is clear? Then similarly, that we have seen with the fundamental matrix, then this will be also basically the line equation of the epipolar lines in the normalized coordinates in the camera frames. And from the definition of the essential matrix and the fundamental matrix, what we can also see is that basically, yeah, this is basically the normalized coordinates, and this is also the transpose of the normalized coordinates, right? So this is basically what we get. This should be 0, and this should be the same with this, right? So what we get is that by the definition of the essential matrix, we can see that the essential matrix can be computed by just multiplying the intrinsic camera parameter matrices into the fundamental matrix. So basically here, we are assuming that the intrinsic matrix of all the cameras are exactly the same, but the same basically thing can hold in the case that when the intrinsic matrix is not the same, of course, in this, but just simplifying the kind of notations. Is it clear? So before we wrap up, like one thing that we're gonna see is that let's think about this case. So as we have seen in the previous slide, now we set the camera parameter for the first view as kind of the identity matrix. And then we are having the camera matrix for the second view. And let's say that this E hat and the E hat prime are basically indicating the epipoles in the normalized coordinates for each of the images. Then since we basically set the camera matrix of the first camera is the identity D matrix, which means that we are treating the normalized coordinates of the first image as kind of the world frame the coordinates, right? Because now the matrix, the camera matrix is basically identity matrix, no rotation, no translation, which means that the normalized coordinates in the first frame is the same with the world frame. So X prime is the same with the capital X, right? This should be so let's see one more thing. So what we can see is that basically, what we also discuss is that the epipole in the second frame was basically the projection of the camera center of the first camera into the second view, right? And now what we are seeing is that we are seeing everything in the normalized coordinates. So we can see is that, and also the normalized coordinate in the first frame is the same with the world coordinates. And so basically, if you project, basically do some kind of transformation of the camera center of the first view into the second view with the extrinsic parameters of the second view, then we can see that the normalized coordinates of the epipole in the second image becomes the same with the translation, obviously, of the second, the camera D matrix. And then one more thing that we're gonna see is that if we also think about the epipolar line of any of the point in the first view image here, that we can see is that basically the epipolar line will be defined as kind of the line which is basically connecting this epipole E prime with the projection of the this point with the secondary camera, the matrix. So if we basically see a kind of the line connecting these 2 points, which is basically the projection like this point into this plane, and also the epipole here, if we find the line connecting these two, and the line connecting these two can be basically computed with the cross product of these two, right? This should be the same with the EX prime, which is also the same the epipolar line, right? So here, basically, what we can see is that if you basically derive all the things, you can see that the essential D matrix actually can be represented with the rotation and the translation of the secondary camera D matrix, the secondary camera frame in this form. So basically, this is basically how we connect the essential D matrix with the camera D matrices. So let's stop here. So what we are going to discuss in the next time is that basically how we can basically compute the fundamental D matrix and the essential matrix from the given the set of the correspondences of the pixels. And based on that, how we can also derive the relative the camera pose. And this will be basically the building block of the kind of the structure from motion the pipeline in terms of that from the correspondences, we get the relative camera pose, and we run the triangulation, and we do some kind of joint optimization. And in this way, that we can do some kind of the 3D reconstruction from the multi-view images. So this is like all the idea that we can do some 3D reconstruction without the neural net from the multiple images. Any questions on this? So as you have seen today, there are lots of kind of new concepts. I recommend you to basically check out, review the things that we discussed today before we discuss the rest of the part in the next lecture. So I will see you next Monday. Thank you.